This is Neil Patwari. In this segment of ESE 471, I'm going to tell you three things about thermal noise. Thermal noise is a random process. I'm going to talk about its autocorrelation function, its power spectrum, and its distribution. In order to do that, I'm going to need to define three things. First, a random process itself is just a random variable that changes with continuous time t. We could also have a random process that was a discrete random process. But I'm going to talk about thermal noise, which is a physical process that operates in continuous time. And I need a mean function for a random process. We refer to it as mu of w here of t. It tells us what the expected value of that random process is for any particular time. We're also going to talk about an autocorrelation function. The autocorrelation function is really closely related to the covariance, plus the product of the mean at time t and the mean at time t minus tau. When the covariance is zero, remember that's the definition of uncorrelated. So a covariance of zero tells us that the two things are generated in an uncorrelated manner. Another thing about the autocorrelation function is that this covariance at a time tau equals zero gives us the variance of the random process at time t. Okay, now that we have those two things defined, we can wide wide-sense stationary. A random process w of t is wide-sense stationary if its mean function is constant with time and its autocorrelation function is constant with time t. Now remember, autocorrelation function is both the function of the time t and the time difference, tau, the time difference between the samples that are multiplied together in that autocorrelation function. So that it is still a function of tau, but it is not a function of t, and thus we can write its autocorrelation function as Rw of tau. This definition is important because when a random process is wide-sense stationary, it has this property. One of the most surprising results that I learned in my random processes course, that for a wide-sense stationary random process, the power spectral density and autocorrelation function are Fourier transform pairs. SW of f, which is called the power spectral density, and it's measured in watts per hertz, and it represents what we would see on average on a spectrum analyzer. A spectrum analyzer shows us the power at each frequency that we choose to measure. So what I need to tell you now is about thermal noise. Thermal noise is a result of having mass in the universe that is above 0 Kelvin. So atoms are moving, they are producing electromagnetic energy across a wide range of frequencies from 0 to much higher than light frequencies. They're producing noise that is then measurable on an antenna. So some properties here is first that W of t is zero mean and Gaussian. It's not a function of time, it is just constant zero across time. And the distribution of W at any particular time is Gaussian for all W. This is the distribution. This is my point 3 on this. Second, it has a power spectral density that is constant across frequency. We refer to that constant as n naught over 2. Now, at some frequency that is at a very high frequency, frequencies we don't deal with in radio communications or even light communications, above that frequency we may have to consider that the power spectral density is not constant. It starts getting lower in amplitude beyond a certain frequency depending on the temperature. And we'll see that n naught, we can write a formula for it as k times f times t naught, where k is Boltzmann's constant. Boltzmann's constant is 1.3807 times 10 to the minus 23rd joules per Kelvin. F, the noise figure tells us how much our receiver multiplies the noise power. And an ideal receiver, we'd have an F of 1, no multiplication. And a realistic receiver, we're going to have an F greater than 1. And T naught is the noise temperature. This relates to the average temperature of what the antenna is pointing at. Okay, so Kelvin is abbreviated as K. we've got a joules per Kelvin, a Kelvin, and something unitless. So this overall noise N0 is going to be joules, which is the same as watts per hertz, because a hertz is 1/2, and watt times second is power times time, which is energy, and thus we get the joules. So that's the power spectral density for thermal noise. Now, the first thing I have to say is that the noise, W of t, is Wideston stationary. That is, its mean and covariance structure doesn't change over time. And what we can then do, based on our theorem, is we can come up with Rw of tau based on the fact that it is the inverse Fourier transform of the power spectral density of the noise. This is our relationship. We can then take the inverse Fourier transform of this constant, n naught over 2. What's the inverse transform of a constant? It's that constant multiplied by an impulse function. So what does that mean? Well, remember that this is related to the covariance minus the mean functions, and these are both 0. So this is equal to the covariance of W of t and W of t minus tau. Essentially, what that is saying is that for any t not equal to 0, the covariance is 0. Okay, the definition of uncorrelated is that it has 0 covariance, and at any time delay other than 0, that covariance is going to be 0. So they're uncorrelated. And because the W of t is Gaussian, that 0 covariance implies that they are statistically independent. So there is no relationship between the values that I'm generating for a time W of t and the values that it is generating for W of t minus tau. What is a graph of something that W of t and W of t minus tau are independent? What does a graph look like there? The key here is that tau can be very, very, very small as long as it's not exactly equal to 0. If I draw any process that has a line in it that connects 2 points and says that they are somehow close together because they're close in time together, it does not work for thermal noise. So in fact, I take from what my professor Andrew Yeagle at the University of Michigan said, is you can't draw any plot for a random process of WT with a continuous line in it. The only way to draw an example plot of WT is to blow chalk dust onto a chalkboard. So in terms of what I want you to know about thermal noise, I want you to know that it is Gaussian, that it has a power spectral density that is constant over frequency, and that its autocorrelation function is constant times an impulse. And because it's a constant times an impulse, if any tau is not equal to 0, then I have independent random noise samples that I would have to generate independently if I wanted to be an accurate representation of what was going on in thermal noise.